In this assignment, we aren't going to complete proofs of limits using delta and epsilon, but we're going to get a better understanding of how you would set up such proofs. So the first comment here in our notes is the idea that you can think of a function reaching a limit if you're able to capture the y-coordinates in a zoom box. So first we look here at our rational function graph, and if we were interested in a point somewhere between 2 and 3, if you did a zoom box around the x-coordinate you are interested in, is it very clear that you could capture the y-coordinates within a zoom box, even if you zoomed in tighter and tighter around your x-coordinate? Can you get the y-coordinate to stay within those values? And compare that to what if you were looking around the vertical asymptote. If I tried zooming in on an x-coordinate here, can you see that we actually don't reach a limit? We have one of the y-coordinates on the opposite side of the infinite discontinuity, way out of the zoom box. So if we look at graph number 3, a piecewise defined function, anywhere we were interested in along the way, even at this corner, if we did a very tiny zoom box, zoomed in on our calculator, the y-coordinates would stay within the window of the calculator, except at the discontinuity. So if you tried to zoom in on a point right here, you can see that we would not capture the y-coordinates from both sides. So the limit doesn't exist because, of course, the left-hand limit and the right-hand limit don't agree. So it's a really very simple concept, and that idea of making a smaller and smaller window on the x-axis to capture the y's vertically is really the way we can think of this delta, this epsilon delta definition. So a classic way of proving a limit involves proving that if the limit is L, then for any value of epsilon greater than 0, so no matter what number you chose as an epsilon value, you could find a delta value that would be also greater than or equal to 0, so that as long as you chose your x values to be within delta units on either side, so a minus delta would be to the left side, a plus delta to the right side. So if you choose an x within this limit, then you are promising that your y-coordinates are going to stay within epsilon units of the limit. So let's use a graph here to see if this makes sense to everyone. So if this is our value of our limit, so if x is going to a, so here in our limit, as x goes to a, so we're interested in this particular x-coordinate, and notice that the arrows show us here that this would be our limit. This would be the y-coordinate. So the limit of f of x there would turn out to be L. So this would be our y target. If we have a limit, that means we know in class we've talked about the highway approaches that point from both sides. So if we go delta units on either side of that x-coordinate, we will stay within epsilon units of the y-coordinate. So in other words, this horizontal line would be L plus epsilon, and this horizontal line would be L minus epsilon. So remember that we did these tolerance window problems already, specifically to get you used to this idea. So if we chose anywhere within that tolerance window, if you chose an x between a minus delta and a plus delta, then your y-coordinates would be guaranteed to stay between L minus epsilon and L plus epsilon. So now we're going to rewrite that a couple of ways. Complete synonyms here. We're not doing anything new. If x is chosen within a delta tolerance of a, then f of x should lie within an epsilon tolerance of L. So as close as you need to come vertically, we can figure out a delta value horizontally. All right, here it is again in 4. Translate into absolute value. Remember, the distance between A and B is the absolute value of A minus B, the distance between those 2 points. Or, of course, because of the absolute value, we could subtract in the other direction. So we're using that here in number 4. Translate into absolute value notation. If the distance between X and A, so the distance between X and A is the absolute value of the difference. If that distance is less than delta, Greek letter delta, then the distance between f of x and L, the distance between f of x and our limit will be less than epsilon. So that is an exact symbolic translation of what we just showed in that graph. And one more translation. If x is an element of the interval that is within delta units on either side of A. So if x is an element of this interval, so we're going to go from A minus D on the left, delta units to the left of A, to delta units on the right of A, so that would be this interval. Then our f of x value will be an element of, and now we're staying within epsilon units on either side of the limit, so that would be L minus epsilon to L plus epsilon. So we can always find a tolerance window. You pick how close your epsilon has to be, how small a vertical distance, and we can find an x horizontal distance delta that would guarantee that the y coordinates stay within that tolerance window. All right, let's take a couple look. Here we've got kind of a joke on the idea of a proof. Clearly not good logic. Cat has 9 tails, no cat has 8 tails. A cat has 1 tail more than no cat. Therefore, a cat has 9 tails. So that fake logic idea here, we want to use good logic as we're doing our delta epsilon tolerances. All right, so I'm going to use the TI-89 model on my calculator here to show you this. So we want to get our function, a parabola. So I'm going to enter this as y1, and here it is already graphed in the diagram. And we're interested in the limit as x goes to 2. Well, we know that polynomial functions are continuous everywhere. Polynomial functions are continuous on all real numbers. Thus, the limit can be found by direct substitution. So the limit as x goes to 2 of f of x is simply equal to f of 2. So let's plug it in here. If we put 2 into our function, we would have 1/2 of 4 minus 1. So 2 minus 1. So our limit is 1. And our limit is numerically 1. And that is the limit we're interested in. So right here in our picture, our limit that we're interested in is right there. No mystery about it. We know the limit is 1 when x is equal to 2. Our question, however, is saying find, well, first, what is the value of L? We just did that. L is equal to 1. Now use your TI-89 to find a delta value if we want to stay within an epsilon of 1/1000th. So I'm going to exaggerate greatly on my graph here. Otherwise, we wouldn't actually be able to see here. So I'm going to call this distance epsilon. So I'm definitely not drawing these lines to scale here, but I want you to be able to see the tolerance. So we're going epsilon units above the limit and epsilon units below the limit. Well, this horizontal line is y equals 1.001. We went 1/1000th above our limit, and this horizontal line down here would be y equals 0.999, 1/1000th below. And then what we're going to be interested in our calculator, and you've done this before, we specifically did this earlier so that when you see these problems, they would seem very straightforward. So there's our tolerance. And now notice that our delta values do not look equal. So I'm going to call them temporarily delta 1 and delta 2. And once we find out those two, then what we're going to do is choose the smaller of the two so that we are guaranteed that we will stay within our tolerance window. So when we've done these problems before, we have, if I can get a highlighter here, we have highlighted this region here as our tolerance window if we can stay within these values. So on our calculator, we're going to be interested in finding these two intersection points. So I've got kind of a crowded graph here. I'm going to call this point A comma 0.999, and I'm going to call this point B comma 1.001, so that I don't have to try and squeeze my answers into that graph. So I'm going to write A is approximately and B is approximately and put my answers over here. Okay, so I clearly know the size of our window. Notice that we're zooming in this point here that we were originally working on. Remember, our x-coordinate is 2 and our y-coordinate is 1. So when I go to my calculator, that's going to help me set up my limits. So I know that my y window has to go from 0.999 to 1.001. So I'm going to go a little bit beyond that when I do my y window. So my x window I know is going to surround 2, pretty close to 2, but I don't know exact. So your window might take some trial and error. Okay, let me switch to the calculator, and I'm going to put 3 things in the calculator. Remember, this original function is going to be my y1, and I will have these 2 horizontal lines be my y2 and y3 in either order. Just make sure you keep track so you remember which is which. So if I bring up my calculator here, and let me resize it to get it into the window. And let me go to the Y editor, and I have already entered these values as my 2 horizontal lines. Y1 is our parabola. And now we want to think about our window. So we're going to go to our window here. And for our x-min and x-max, we're not exactly sure, but we know we want it to be very close to 2. So I might put, for my x-min, I might put 1.9. My calculator's jumping around, sorry. And if I go down to the x-max, let's go to 2.1. I might be able to, that might be much wider than we want. And our y-min and y-max, we know where we put those horizontal lines. So I'm just going to go a little bit below that 0.998. And for our y-max, I'm going to go just a little bit above 1.002. And then let's go to our graph and see how our window does. Oops, I went to table instead, sorry. Let's try that again. Okay, so we actually, remember, are so zoomed into our parabola that looks like it's nearly a vertical line, but remember that's part of our parabola, same as the picture on our paper here. So now we're interested in the intersection points, so I do F5, choice 5 to find intersection, and I have to answer the 4 questions. Is Y1 one of the curves you're interested in? Yes, it is, so I'll hit enter. And is Y2 the other one? Sure, I can do these in either order, so I'm just going to hit enter for yes. And then right underneath our writing here, we want to get to the left of our intersection point for our lower bound and hit enter. And then I'll use the right cursor to get to the right-hand side of our intersection and hit enter. And there is our intersection value. So our x-coordinate is 1.999499. So let me transfer that to my paper. So that would be our intersection point for my A, 1.9994999. How close do you have to be? Enough so that we can see our delta value. So for now, I'll keep that many digits. And now let's go back and, well, maybe while I'm here, we could show you what you needed this for. What we needed this for now for our A value is to find the delta 1 distance. So how far is that value from 2? So we're going to subtract that from 2 to find our delta 1 distance. And I'll write both of those in at the same time in a minute. Let's go back to our calculator and find our other intersection point. So we'll find B, the intersection of graphs y1 and y3. So on our calculator, I'm going to do F5 again. And choice 5 for intersection. Is y1 one of the functions I'm interested in? Yes, it is, so I'll hit enter. And I don't want y2, we just did that one, so now I want to jump up to y3. So either the up or down arrows, and if you guess wrong which way, just do it again. So y1 and y3. y3 is now my second curve, so I'll hit enter. Move the cursor to the left of the intersection and for a lower bound, and hit enter. And then move the cursor to the right side for an upper bound. And this will give us our value of B. And I will transfer that to my paper. 2.000499. Okay, so now we can find our distances. Each of these values, how far are they from our original x coordinate of 2? So our delta 1 distance, 2 minus that value, would be 0, 0, 5. And if we go with 6, 7 decimal places, and our delta 2 value, how far is this value from 2? 1, 2, 3 zeros, and a 499, if I keep the same number of digits. So how do we choose our delta value? We want to guarantee that we stay between those horizontal lines. So the safe choice is to choose our delta value to be restricted smaller than those two values. So my conclusion then is I will choose delta to be approximately 0.004, and we might as well keep the accuracy we have here. We could be less accurate and still be okay, but we'll choose delta to be the smaller of those values to ensure that f of x is an element of our interval from the limit was 1 minus epsilon to 1 plus epsilon. So we stay within our vertical tolerance if we choose delta, if we choose a distance small enough away from our limit of 2. All right, so there's our conclusion. Okay, so do we understand? Try filling in this graph here so that you get the idea. Again, our limit as x goes to a is going to produce a limit L. And how can we stay within our tolerance window? We would want to choose a distance delta on either side of a so that if we pick our x value between a minus delta over to a plus delta, if we choose an x coordinate between those two values, we will stay within epsilon units of L. So that would keep us between L minus epsilon and L plus epsilon. So to make sure you understand, delta is the horizontal tolerance, epsilon the vertical tolerance. All right, I will try to give you the basics of these next tolerance window problems. So if we're interested in x cubed as x approaches -2, so I'm really, and I'm going to exaggerate here in my graph, we know what the cube function looks like, and at -2 we know our value of the limit is -8. So this is our limit value A. And our question is, how can we stay within 1/100th on either side? So we want to set up our tolerance window. And again, I'm greatly exaggerating the distance here. So if we want an epsilon value of 1/100th, then this line in my calculator, I'm going to enter the horizontal line, -7.99. And I want to stay between that epsilon value on the other side of 0.01. So this line in our calculator would be at -8.01. So we're going to enter our f of x as our y1 function, or you could put it wherever you want to in your calculator, of course, and I can enter these two lines as our y2 and y3. Then what we're interested in is finding the x coordinates. So we've got a pretty small delta value here. Let's see if I can make some green lines between those. And I maybe had to kind of exaggerate. I kind of missed my -2. Should have been between those two lines. There's our -2. So this value and this value would be our tiny values of delta. So they might turn out to be different. Delta 1 and delta 2 might be two different distances, and then we're going to choose the delta that is the smaller of those two units. So I'm going to enter that in my calculator, and then I'll come back and show you the answer. So I've entered in my three functions, the x cube line, and then the two horizontal lines on epsilon units away from -8 on either side. And now before I go graph, I should think about what window I want. So we already have a pretty good picture here. We know that our x is very close to -2, so I'm not sure exactly where I want to put that. So I might have to zoom in even more, but it looks like it's going to be very small. So I might begin with an x minimum of, let's say, -2.01. Maybe just 2.1. You can decide how close you think that's going to be. I might be zooming in too closely, and then I might pick -1.99. And our y-min, we're way down there at -8, and we know our horizontal lines, we want our horizontal lines to be visible. So my y-min, I'm going to go a little below. So I'm going to go to, say, -8.02, and my y max a little bit above that line, -7.98 perhaps. So the question is whether I've been too stingy on the x min, x max. So we'll find that out. We might have to come back and redo our window. So let's go look at our graph and see whether we see a tolerance window. And that actually gave me some nice space to work with. So now I'm ready to find my intersections. So F5 intersection, and you'll start doing this very quickly. Yes for graph 1, yes for graph 2, yes for a lower bound, move the cursor, and there's my upper bound. And then we can transfer that -1.99166 onto our paper. After I transfer that to the paper, and I'll show you that in a minute, then I would want to come back and I'd want to do F5 intersection, and this time the intersection of y1 and our other function y3. So once you use your up-down arrows to get it to show 3, then hit enter, and left cursor to be to the left of your lower bound of your intersection, and move the cursor to an upper bound around the intersection, and then we'll come up with our second boundary here. This is the x coordinate of the other intersection. So I'm going to transfer that to my paper, and I'll have two different values of delta. All right, to save some time here, I've already got that done on the Word file that you guys know will always be available to you. So here were our intersection points between those two graphs. So I let A be the intersection, the lower intersection, and B, but you don't have to do that the same way. I just use this A and B idea here to save space because our graphs can get very full of information. So our delta values, the distance from -2. So subtract each of these, find the distance from -2. There's our delta 1 and our delta 2 value. So and use your calculator to subtract if you're not, if it's not real simple. And then just choose your overall delta value to guarantee you're within the epsilon units from the limit. So choose the smaller of the two values as your delta. All right, and let's take a look then. You're going to repeat the process here for a natural limit function. So you're going to put this in as your y1, and this time our epsilon value is 1/10. So hopefully you can say that the natural log function is continuous not everywhere, but from 0 to infinity it is continuous. So it is definitely continuous at x equals 1. That's what we're interested in. And you know that's our key point on a log graph. So we want to stay within 1/10. We want to stay vertically within 1/10 of 0. So notice your two lines that are epsilon units above and below 0. So you're going to again put these in as y2 and y3. And then I let A be the intersection coordinate down here, and I let B be this intersection coordinate, the larger of the two. So then I'm interested in the delta distance. How far are those intersections from our x coordinate of 1? And then I wrote this differently, simply so you would see that there's not just one way to give your answer. Why are we choosing delta? Why are we choosing that delta distance? If you stay within that much of your x coordinate, which was A, in this case 1, if you stay within that distance of 1, then your y coordinates will stay within epsilon units above and below your limit. Here our limit happened to be 0. Okay, so that's just a beginning introduction to delta epsilon proofs. There's a lot more once we start doing them with algebra rather than with specific tolerance numbers.